Welcome back for the fourth and final installment of the AP ECE Chapter 17 Spontaneity of Reaction Problem Set. I'm Mr. Wilkosz. Let's look at 65. In problem 65, you're given a reaction, carbon monoxide reacting with three hydrogen gases to give an equilibrium, methane and water. You're given a K for this at a certain temperature, K your equilibrium constant, and a K for this at another temperature. And then you're asked to find the Gibbs free energy change at both temperature values. So you can actually relate Gibbs free energy, delta G naught, to the equilibrium constant K by the equation delta G naught equals negative RT ln K. So just plug in both temperatures, plug in both K values, and then solve out. At the 473 Kelvin temperature, you have a negative 103 kilojoules Gibbs free energy. It's spontaneous, and it's still spontaneous at the other temperature, 533 Kelvin, but less so as the number is less negative. Let's check out problem number 67. In problem 67, you're given a Gibbs free energy formation for barium sulfate, a rather insoluble substance, and you're asked to then find the KSP. It's sort of like the reverse of the previous problem, so you're still using delta G naught equals negative RT ln KSP, but you have to rearrange it to solve for KSP, so it becomes e to the negative delta G naught divided by RT. You have to solve for your delta G naught because you're not given that, so use the tables in the back of the book to find what a Gibbs free energy would be for the formation of this from its standard pieces, and plug that in. And then you do the calculation to find KSP, and through this means of delta G naught equals negative RT ln KSP, you get a 1.0 times 10 to the negative 10th. Chapter 16, if you compare back to it, the precipitation chapter says 1.1 times 10 to the negative 10, so that's pretty good. Let's take a look at the next problem. Problem 69. In problem 69, you're told that a 0.218 molar solution of a weak acid that is abbreviated as HX has a pH of 4.57 at 25 degrees Celsius. And then you're asked for what is the Gibbs free energy change for this particular dissociation. So like always, I recommend writing an equation. HX dissociates into H plus and X minus. Write a Ka expression for that with the products H plus and X minus on the numerator and HX, the undissociated acid, in the denominator. Then you start to plug in some values. Now for this particular arrangement here, one more calculation has to be made. They give you the pH of 4.57, so you have to find the concentration of the hydrogen ion as 2.69 times 10 to the negative 5th molar. That can get plugged in here, and then it gets squared. This is a squared sign right there, because you've got an equal concentration of H plus and X minus as this dissociates. And then you're doing 0.218, your original concentration of the solution on the bottom, minus your concentration of the ions that dissociated, which is essentially 0, so you can just kind of ignore it. And then you get a value of 3.32 times 10 to the negative 9th for this Ka. So then plug that in to RT ln K, and this is just a Ka. So now we're connecting this chapter about spontaneity reaction back to our acid and base understanding. And when you plug in that number, do the natural log of the K, you get 48 kilojoules as the Gibbs free energy. So there's a positive value, so it's not a spontaneous reaction. Let's check out the next problem. Number 73. In problem 73, you're asked to calculate the Gibbs free energy change for at 25 degrees Celsius for the reaction 2-methane gives you 2 C2H6 plus H2. So that's a 6 right here. And then asked to decide how likely this is. So you calculate that by doing the products minus the reactants. You get those Gibbs free energy values out of the table. And you'll find that this is a non-spontaneous reaction. When you sum everything up, it's a positive value, 68.5 kilojoules for this particular reaction. If you're then asked in part B to couple this reaction with a different reaction, H2 plus a half mole of O2 gives you H2O, which has a negative Gibbs free energy. You can sum up those Gibbs energies and find out what the Gibbs free energy would be for the combined reaction. And this is what happens with a lot of reactions. A spontaneous reaction can be coupled with a non-spontaneous reaction, and the energy released from the spontaneous reaction can be used to drive the non-spontaneous reaction. So this non-spontaneous reaction in part A can be driven by the spontaneous one with a negative Gibbs free energy value in part B. So this one would become spontaneous. Look, it's got a negative 160.1 kilojoules energy.